Block 1. The Cosmic Illusion. Why Empty Space Isn't Empty. Hello, Cosmic Explorers, and welcome back to the channel. Take a moment and picture the universe. What do you see? Perhaps you imagine brilliant burning stars, billions of them, scattered like diamonds on black velvet. You might see the swirling, majestic arms of spiral galaxies, or the ethereal glow of nebulae where new suns are being born. You see planets, asteroids, comets, a grand cosmic ballet of light and matter. For centuries, this has been our picture of reality. We looked up at the cosmos and assumed that what we could see was, more or less, all there was. The glowing, luminous stuff was the universe, and the vast, dark stretches in between were just that, empty space, nothingness. But what if I told you that this picture, the one we've held for all of human history, is a profound illusion? What if the real story of the universe isn't written in the stars, but in the crushing, overwhelming darkness between them? Today, we are diving headfirst into one of the most mind-bending and revolutionary discoveries in all of science: the fact that this empty space isn't empty at all. In fact, it is home to more mass and more energy than all the stars, galaxies, and visible matter combined. This isn't a thought experiment or a slice of science fiction. It's a conclusion forced upon us by decades of evidence, a scientific paradox that has completely reshaped our understanding of reality. To grasp the sheer scale of this mystery, we first need to understand what we see. Everything you've ever touched, seen, or interacted with is made of what scientists call baryonic matter. It's the protons, neutrons, and electrons that form atoms, which in turn build you, me, the Earth, the Sun, and every single star in the night sky. For a long time, we thought the universe's inventory was simple: a whole lot of baryonic matter and a whole lot of empty space. But as our instruments became more sensitive, a terrifying cosmic accounting error began to emerge. When we add up all the mass from all the stars and all the galaxies, and all the gas and dust clouds we can detect, we arrive at a startling number. All of it, every sun, every planet, every nebula, makes up less than 5% of the total mass and energy of the universe. Let that sink in. Imagine the entire cosmos is a vast, deep ocean. For our entire existence, we've been sailing on the surface, marveling at the waves and the shimmering light, thinking this was the whole ocean. But now, we've discovered that 95% of this ocean is an invisible, unknown substance lurking in the depths below. Its presence only detectable by the strange currents and ripples it creates on the surface we can see. So, what is this other 95%? Where is it hiding? It's hiding in the void itself. This forces us to ask some truly fundamental questions. How could we have missed the vast majority of existence? What is this invisible substance that so dramatically outweighs everything we know? This discovery has launched modern physics into a new era, a quest to map the unseen. We're like detectives who've arrived at a crime scene where all the major players are invisible, their actions only inferred from the clues they leave behind. The cosmic mass energy budget, the official inventory of the universe, now tells us that ordinary matter is just a tiny slice of the pie. The rest is divided between two enigmatic entities that have been given appropriately mysterious names: dark matter and dark energy. They don't shine, they don't reflect light, and they don't seem to interact with our world in any way we can directly perceive. Yet their influence is absolute. They are the puppet masters of the cosmos, shaping the evolution of galaxies, dictating the structure of the universe, and controlling its ultimate destiny. Prepare to discover the universe's biggest secret, lurking in the shadows of the void. Block 2. Dark matter, the universe's invisible architect. So if 95% of the universe is invisible, how on earth did we figure out it was even there? The story begins not with a sudden discovery, but with a nagging, persistent anomaly, a cosmic puzzle that just wouldn't go away. In the 1970s, an astronomer named Vera Rubin was studying the rotation of spiral galaxies. The logic seemed simple. Just like in our solar system, where the inner planets orbit the sun much faster than the distant ones, the stars in a galaxy should do the same. The vast majority of a galaxy's visible mass, its stars, gas, and dust, is concentrated in the bright central bulge. Therefore, stars on the outer edges, far from this central mass, should be moving much more slowly. If they moved too fast, the galaxy's gravity wouldn't be strong enough to hold on to them, and they should be flung off into the cold emptiness of intergalactic space. But when Vera Rubin pointed her spectrographs at the Andromeda Galaxy and others, she found something that defied all expectations. The stars on the outer fringes were moving just as fast as the stars near the center. This was a complete violation of Newtonian physics. To explain this, picture a spinning merry-go-round. The kids holding on near the center don't have to grip very tightly. But the kids on the outer edge are being pulled outwards with incredible force. If the merry-go-round spins fast enough, they'll fly off. The stars on the edge of galaxies were spinning fast enough that they should have flown off billions of years ago. The fact that they haven't means there must be an enormous amount of extra gravitational pull holding them in place. A pull coming from a massive, invisible source. This was the first major piece of evidence for what we now call dark matter. The galaxy rotation curves didn't lie. Galaxies seem to be embedded in a vast, spherical halo of this unseen substance, a kind of invisible scaffolding whose gravity dominates the entire structure. This dark matter halo can be 10 times more massive than all the visible stars within the galaxy itself. But the evidence didn't stop there. The next clue came from one of Albert Einstein's most profound predictions. Gravity bends light. According to his theory of general relativity, massive objects warp the fabric of space-time around them. Light, which normally travels in a straight line, will follow this curvature. This effect is called gravitational lensing. Think of it like looking at a candle through the distorted base of a wine glass. The image of the flame is bent, magnified, and sometimes even appears in multiple places. Astronomers realized they could use this effect to weigh distant galaxy clusters. By observing how the light from even more distant background galaxies is distorted as it passes through a cluster, they can calculate the cluster's total mass. And once again, the numbers didn't add up. The lensing effect was consistently far stronger than could be explained by the mass of all the visible galaxies in the cluster. There was 5 to 6 times more mass than we could see, all of it contributing to the gravitational lens. The smoking gun for this phenomenon is the bullet cluster, where 2 galaxy clusters have collided. The ordinary matter, the hot gas, smashed together and slowed down in the middle. But the gravitational lensing shows that most of the mass passed right through without interacting at all, separating the invisible dark matter from the visible baryonic matter. So what is this stuff? The honest answer is, we don't know. We know what it's not. It's not just dark clouds of normal matter because we would have detected them. It's not black holes or neutron stars, as we don't see enough of them to account for the mass. The leading candidates are hypothetical, exotic particles that barely interact with our world. The most popular are called WIMPs, or weakly interacting massive particles. These theoretical particles would have been created in the early universe, and they pass through you, me, and the entire Earth as if we were ghosts. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays, in a global race to capture the first direct detection of a WIMP bouncing off a nucleus. Dark matter, which makes up about 27% of the universe, is the silent architect. It was its gravity that first pulled matter together in the early universe, forming the seeds of galaxies and the vast cosmic web we see today. Without it, we simply wouldn't be here. But as strange as dark matter is, it's only the smaller piece of the invisible puzzle. That's it. Block 3. Dark energy, the force tearing the universe apart. After discovering that an invisible substance called dark matter was holding the universe together with its immense gravity, you might think the biggest cosmic mystery had been solved. But the universe had another, even more profound secret in store. For most of the 20th century, cosmologists debated two possible fates for our universe. Either there was enough matter that its collective gravity would eventually halt the expansion from the Big Bang and cause everything to collapse back in on itself in a big crunch, or there wasn't enough matter and the universe would expand forever, but at a continually slowing rate. In either scenario, gravity was the undisputed champion, the dominant force on a cosmic scale. But in 1998, two separate teams of astronomers made a discovery that was so shocking, so utterly contrary to all expectations, that it blew the doors off of cosmology and won them the Nobel Prize. They were studying a specific type of stellar explosion called Type Ia supernovae. These supernovae are incredibly special because they act as standard candles. They are the lighthouses of the cosmos. Because they all explode with almost exactly the same intrinsic brightness, we can determine how far away they are by measuring how dim they appear to us. The plan was to look at very distant supernovae to measure how much the expansion of the universe had slowed down over billions of years. But they found the exact opposite. The distant supernovae were even dimmer, and therefore even farther away than they should have been in any universe where gravity was in charge. The only way to explain this was if the expansion of the universe wasn't slowing down at all. In fact, for the last 5 or 6 billion years, it has been speeding up. This was a revelation of staggering proportions. Something was actively working against gravity, a mysterious repulsive force that was pushing galaxies apart at an ever-increasing rate. This something was given the name dark energy. It is a form of energy that seems to be inherent to the fabric of space itself. As space expands, more space is created, and with it, more dark energy, leading to a runaway feedback loop of accelerating expansion. If dark matter is the universe's architect, building structures with its gravity, then dark energy is its demolition crew, relentlessly tearing everything apart. When we add dark energy to the cosmic budget, it is the undisputed king, making up a staggering 68% of the total mass energy content of the universe. This leaves dark matter at 27% and the stuff we're made of at a paltry 5%. So what is it? The leading idea is that dark energy could be the cosmological constant, a concept Albert Einstein himself proposed in 1917 to keep his model of the universe static, before observational evidence showed it was expanding. He later called it his biggest blunder, but it now seems he may have been right for the wrong reasons. This idea suggests that even a perfect vacuum, stripped of all matter and radiation, possesses a fundamental intrinsic energy. It's the cost of having space. This energy has a negative, repulsive pressure, and it's this pressure that drives the cosmos apart. The implications of this are profound and determine the ultimate fate of everything. If dark energy continues to dominate, we are heading towards a future known as the Big Freeze or heat death. As the expansion accelerates, galaxies will be pushed apart so fast that one by one, they will cross a cosmic event horizon and disappear from our view forever. Eventually, our own local group of galaxies will be all that remains in an otherwise empty, invisible universe. The cosmos will grow ever colder, darker, and more desolate until the last stars burn out, leaving nothing but a cold, silent void. We find ourselves in a truly bizarre situation. We live in a cosmic ocean, aware of only a tiny fraction of what it contains. The two most dominant components of our universe, dark matter and dark energy, remain complete enigmas. They represent a fundamental gap in our knowledge, telling us that our current theories of physics are incomplete. The greatest mysteries are not in the distant stars we can see, but in the very fabric of the empty space between them. What do you think dark matter and dark energy truly are? Let us know your theories in the comments below. Subscribe for more cosmic revelations, and we'll see you in the next one.